Okay, so today we'll be talking about operational amplifier and negative feedback. Trying to see if we can get through the entire slides. If we can, then next week we won't have any discussion. From that point on, we'll just be, I'll just be in HESI for office hours. You guys can come by, ask me final project questions or exam questions, okay? So, first of all, the purpose of having an amplifier is that you might have already encountered that in your lab. Your ESP32 is unable to drive such current into a speaker to make sound, so it's good to have an amplifier that does it for you. It'd be the same thing for you. It's like a power steering in your car. When you're driving on a highway, you're probably unable to control your car completely with your bare hands. So it's good to have a power steering where you use hydraulics to help you turn. It's basically you put in a little bit of turning signal, you put in an input signal, and the hydraulic amplifies it for you by putting a lot of pressure on the mechanical system of the car. It's the same idea here, except that it's electrical. A simple amplifier, we use a block with the square called A, and basically A is your gain, and your output is your input multiplied by that gain. I actually use this. The output is your input multiplied by this gain. And you can see that it's reflected over here. Whichever your original graph is, the output amplifies it and makes it louder. Generally, amplifier makes things louder. I don't know about making it quieter. I don't know if that could be possible. I have to think about it. So if you model a simple amplifier, that's basically you have an input, like I said, input, and you have this, op amp inside. You have this amplifier inside, and on the other side you have another resistance, and your gain multiplied by your input will be your output. So then you can represent that with this, something like it's a dependent source, meaning that its voltage and the current characteristics is it depends on what's being fed into it. Okay. Any questions so far? Should be pretty intuitive. And then after that, you have the differential amplifier, which is you take the difference of here and here. You take the difference between VI1 and VI2, and the gain and your final voltage output will be whatever the gain you have multiplied by the difference between your VI1 and VI2. So let's say if your VI1 is 5 volt and your V2 is 3 volt and your gain is 50, then your final output will be V0 equals to 50 times 5 minus 3, which is 100. Does that make sense? This is called differential voltage amplifier. And this is actually the building block of operational amplifier. We'll see in just a second. This is exactly what I just said, but just to clarify the terminology, this is called a non-inverting input. This is called the inverting input. And you can memorize it easily by thinking about negative meaning something negative, something inverting, not positive. So positive will be non-inverting. Negative will be inverting positive to negative. So if that helps you. I don't know if that makes you more confused, but negative, just remember negative is inverting input. And I think the reason is because the real reason is because if you choose the negative part to be your input, you put the signal in your inverting input, so-called, and you do your amplifier that way, your output signal will be flipped in terms of its, it will, like if you put in a negative voltage in there, your output will be an amplified version of it, but on the other, like negative voltage. So if you put in, so you would never get, so if you use your inverting input as your actual input, your output is actually the opposite direction of it, opposite sign. So still the same gain, but opposite. But if you were to choose non-inverting input, then your output would still be the same number, but in the same sign. Does that make sense? So the output is the same thing, except that, yeah. Okay. And then let's try a quick example. I want to hear people yell the equations out so we can do it. So we have VI1 here, we have VI2 here with a gain of 1,000. What will be the output signal look like? What does V naught look like? Just shout the what's the first element? What's the amplification we have here? 1,000. That's right. Multiplied by the difference between the two inputs. So it will be, first one is what? VI1 is 0.006 cosine, yep, 10t, minus, yep, that's right, cosine 10t. and you can realize that you can basically extract them. So so basically at the end of the day, you have the same cosine 10t. It would just be 1,000 cosine 10t. The inside will be 0.006 minus 0.004. That gives you 0.002, right? And then 0.002 multiplied by 1,000 gives you what? 1, 2, 3. Becomes 2. So the final V naught will be 2 cosine 10t. That's right. Okay. Does that make sense? This will be your final V naught output. You just put in the V1. And you can see how the big picture here is that the difference between these two are like 0.002 cosine 10t. And your output all of a sudden gets you 2 out of cosine 10t. And it's like you're just basically getting freebie energy out of it, right? But that's not true because your differential amplifier gets energies from somewhere. It has a power source. You need a power source to power it. So you're not getting free energy. But the idea here is that you can put a very small amount of input signal, for example, your ESP32 signal, and you can get a very large output that you can directly feed into the components you can run. So you don't have to rely on ESP32 having a very powerful pin to drive your components. You can use external components to help you. That's the idea. So how can we get more out of it? So if we can control the gain by using some sort of circuit components. So if you put an R1 here, put an R2 here, you can have a sort of different output if you take the differential differences and then they have different grounds. But we'll look into that in the following slides. So any question with this so far? How the amplification is calculated? Let's see where we at. No? All right. So let me see where I am. Okay, we need to go faster here. 10:20. Oh, question.
Is it possible to use this? Is it called operational?
This is just differential. We haven't gone to operational yet, but I will talk about it in a second.
Is it possible to use a differential amplifier with only one input signal?
With only one, well, differential amplifier is all about the difference, right? So if the other port is wired to the ground, then yes. Yeah, so yeah, there you go. So, does that answer your question? Yeah, but you have to have when you're talking about not putting a signal in, I guess you're talking about putting it into ground. Otherwise, if you have a differential amplifier and you don't put anything in that terminal, you actually have no idea what that terminal is. So it might give you something really strange. You have no idea where it is. Yeah. So the operational amplifier is a special type of it. It gives you a lot of control over the amplification of signals. And like I said earlier, you're not getting free energy, obviously. You're going to put in your own large power source that is able to supply the current and power you're about to control. So if you don't have that, you're just putting your input signal, nothing's going to happen. Right? There's no such thing as a free lunch. So the characteristics of op-amp is that so for this class, we'll probably mostly analyze an ideal op-amp. The nice thing about the ideal op-amp is that we have infinite gain, we have infinite input resistance. I'll talk about what that means. Infinite gain means it ties into the idea that we're making V1 equal to V2, okay? But we'll talk about it in just a second. Infinite input resistance, so no current, so that your input current in your circuit analysis, if if you see this node coming in here, like that, that just means you only have the voltage coming in. You can assume that no current is coming in. It is an open circuit. This point is an open circuit. This point is an open circuit. When you see that so let's say take an example of this, right? You can assume this to be open circuit. Just the voltage get fed in there. No current going in there. Same thing as here. No current. Okay? And this one is no resistance. Everything gets put out. So zero output resistance. So whatever current you produce, everything flows out. There's nothing that is being taken away from the resistor. Unless you put external load, which is a different story. Okay. What truly happens behind the scene is there's about 30 transistors and resistors put together to make the op amp happen. But we'll just abstract that away because it's out of scope of the class. I think maybe some of the EECS class will talk about it, how op amp is actually made. But for this class, we just need to know that, you can see that. So with the infinite gain, what can we do, right? We thought like if we reflect back to a couple slides ago, we talked about the output equals to your gain multiplied by the difference between your terminals, right? We say that your terminal have to be equal to each other because in order to have because if this is 0, then for this to make up for the difference, you have to have infinite gain. So that's why I talked about earlier, amplification can be infinite because your VI1 and VI2, we make these two terminals to be the same. So whichever voltage gets fed into VI1, VI2 has to be the same thing. They have to equal to each other. Okay? Anything unclear so far? VI1 has to equal to VI2. So their difference is 0, but and then your amplification is almost infinite, so it comes out to be a finite voltage. I know that sounds really strange, but that's how the ideal op amp will work. In real life, you will have a slight difference. You'll have a slight difference between these two ports, and your gain will still be huge. But you have a slight difference between these two, and it acts like a differential amplifier. But for the ideal case, we just say that they're perfectly tracking each other, right? You put in one, the other one immediately follows suit. Does that make sense? And it's an ideal case. You just assume that, and it will make sense to you as you do more practice. So now we have all these tools in our toolbox. How can we actually make it to work? So one of the things we do is that we do this thing called negative feedback. We talk about negative feedbacks a lot. It's a negative feedback loop. If you sleep late and you wake up late, second day you're not tired. You're not tired until 3 a.m. and you sleep late again, wake up even later, which is like what I do honestly now. So it becomes a negative feedback loop, right? But the idea is that your output affects you back into your input. And the idea is that you can, if you take your output and pass it through a resistor, we'll talk more about this resistor, feed it back into your input, you can actually control your input. And the idea is that whatever voltage is here, after you pass it through the resistor, it's going to directly define what the input is going to be. And your input over here is also defined. So ultimately, you are controlling your output signal by feeding it back with a certain resistor. And if you define your resistance value well, you can control what the output voltage can be. That makes sense? Okay. So that's called negative feedback because in this case, your amplitude is not set to infinity anymore. You're controlling it to have a finite output of voltage. And I think actually I made a little mistake previously. Here, you will have infinite gain, so that if there's ever so slightly a difference between two terminal, it infinitely blows up. So that's why V1 and V2 cannot be different. Otherwise, you'll have infinite voltage coming out of it. So in negative feedback, you feed your output back into your input, so that you can control it. Okay, we'll get a little intuitive things going on here in just a second. So how do you analyze such op amp, right? So you like I said, we make use of this infinite gain, infinite input resistance, and zero output resistance characteristics, and then like, drives the difference between the V1 and V2. Its purpose is to make sure V1 and V2 goes to 0, so you can settle down into a finite state. Okay, so in this case, this is actually called a unit gain buffer. Unit gain buffer. The idea is that you're feeding your output voltage directly back as your input, forcing this to also be your output. So that way, so actually what's going to happen is that your V in here is going to define what the output is. It's very interesting. So we'll do an example real quick here to show you how that works. Okay. This is what we saw earlier. You're feeding a signal, you're feeding your output V naught here, sort of back into your V in. Let's just say this is V minus, this is V plus for an analysis purpose. And you want to find what V naught is, right? So first thing you do is you say, let's try around and see what we can find here. What do we know, right? There's a ground. That means that V plus has to equal to 0. That's right. And by the same token, since V minus equals to V plus, that also equals to 0, right? Oh, that means like, okay, interesting. Well, I'm just feeding 0 volts in there. How am I going to control the voltage, right? This is where op amp is truly amazing, is the fact that you can still control the output signal, even though both your input ports are at 0 volt. And how do I do that? We take this portion of the circuit out, and let's look at it, okay? This is a minus. You have an input. You have an input voltage. You have an input, resistance called R1. There's your V in. And then the same port, R2, goes into your V naught. Okay? And this is 0 volt. This looks very much like the equation. So we can say that if we define this with the I1, we define here as I2, and let's actually make a direction. Let's just assume direction goes this way. Well, but you have to have the same direction. So direction goes this way, right? Because none of your current is going to go into a 0 volt. So whatever flows in must flow out, right? So I1 will have to equal to I2. Does that make sense so far? Okay. So, and V naught minus the difference between V naught and 0. So V naught minus 0 over I2 is equal to 0 minus V in over I1. Make sense so far? This is just your voltage just the voltage difference divided by currents. Resistance, gives you the current. Does that make sense? Ask questions right now if you're confused. I'll zoom in here just so you can see better.
So should it be R1 and R2 in the denominators?
Oh, yeah, my bad. Sorry, I'm so sorry. Yeah, R1 and R2 and R1. Yeah, there you go. Because let me also flip this. So it's I2 equals to I1, and by definition of voltage resistance, I equals to V over R, right? So your voltage difference divided by your resistance gives you current. Okay, so where does that lead us? So cancel out the zeros, we get something like V naught over R2 equals to negative V in over R1. And then we are looking for your closed loop gain, right? Your gain is V naught over V in. So basically move the V in over down. Move the V in over down here. Move the R2 over up there. And then we should be able to solve this problem. So we'll have V naught over V in equals to negative R2 over R1. Right? Yeah, I think so. Yeah, I think so. Okay. So yeah. So this is how. So you see in this case, if you are able to define if you're able to define your R2 value and your R1, so let's say whatever your V in is, if you put your R1 to be 1 ohm and your R2 to be 2 ohm, then your gain becomes A equals to negative 2 over 1 is 2. So you gain, negative 2. You're making the signal double the signal strength, but you're flipping the sign. Does that make sense? And if you define your R1 to be 0.5 ohm, okay, then it actually becomes 0.5 over 1 gives you negative 0.5. So you have the signal strength and you're flipping the signal. Unfortunately, with the negative feedback, you cannot flip the sign of the signal because you cannot choose a negative R value, right? R has to be positive, so you have to choose a positive, so you have to deal with it. We will talk about how to not get a negative output signal in just a second. Does that make sense so far? How you're choosing that? And this is a special case where your wiring is directly to ground, okay? That's how you control it. In other cases, you might not wire to ground. So over here, you might not have V0 minus 0, you might V0 minus like some other V reference, right? But the idea is still the same. You're using the same reference voltage, okay? All right, any questions? This is where we at, 15, okay. 33, okay, we're on track, okay. So here's another question we can take a quick look at. I'll just go through the example so you have a understanding of it. We have the op amp here. Can anybody tell me immediately what are some key observations we can make here? What can we deduce right now just by looking at the circuit, especially around where the op amps is? I'll give you a hint. What would V plus equal to? 0, right? Because it's ground. All right, so immediately we know V minus is 0. That's right. Okay, so we mark that out. This is 0, and over here another 0. Okay, we might have to make some notes here. So this is V naught, right? And then V naught. This is still V naught. We don't know what this is. We can say this is Vx, whatever name, right? This is Vy, but Vy is 0 already, so this part is already 0. Does that make sense so far? 0, right? Same wire, right? Okay. So now we're looking for yet again our V out over V in, and let me make a new page actually. So we're still again looking for V out over V in. So your couple equation we can have V in. Let's write that out. V in. Let's just define this to be I1, right? V in minus R1 I1 equals to 0, right? Does that make sense so far? Okay. And then we have another current. Since we define it this way, whatever comes in has to come out. So we'll define current the opposite way over here. Okay. And voltage, since this is ground, we can just say voltage flows like this. How about that? Okay. So we'll say that this way. This one is I naught, and this is I2, and then combined I have I3. Okay. And then we got a couple other currents coming here, and because I2, and then I2 is equal to I1, because whatever, you cannot have any current here. There's no current coming in here. The only thing here is voltage. So I1 has to equal to I2 because there's only one path for the current to flow. That's right. Okay, so in this case, 0 plus, I guess, I2, R2 equals to Vx, right? And then at the same time, Vx minus I3R3 is 0, which is this loop right here. Ow, I just erased all of my stuff. This loop right here. And then lastly, we look at this part. V naught minus R4 I R naught, yeah. equals to, I should have named this, I'm going to name this our I4, okay, just so we have the naming convention same. Okay, that gives me Vx. Now you look at and then this one, I2 can actually be transformed into 0 plus I1 R2 equals to Vx, because, there's no difference, right? I2 is I1 is R2. Okay, so you have, how many unknowns do we have? We have Vx is our unknown, I1 is our unknown, I2 is our unknown. No, actually, no, you can cancel this one out. I3 is our unknown, and I4 is our unknown. Actually, wait. 1, 2, 3, 4. Wait, am I missing an equation? I think I'm missing an equation. Hold on. Oh yeah, but hold on, what? Shouldn't be a. There's like a. Give me a second. Why is there like a. I don't understand. Because there's 4 equation should be you have the same number of variables, same number of equation, and then you'll be able to solve it. That's interesting because it didn't solve that out for me. Weird. So, sorry, I forgot the last equation. I3 is equal to I2 plus I4, which is I1 plus I4. Okay. Current junction law. Okay, so now you have how many? You have 1, 2, 3, 4, 5. You have 5 equations. You have 5 unknown variables, and you put them into a matrix, and you solve it, right? And you solve it at the end, and then you'll get your V out, probably in terms of your Vn, and then you just the V out equal to something, and then you move the Vn over. That's your game, right there. Okay. So due to the interest of time, we'll probably skip this part. But then after that, you can see how this is being controlled, okay? This is a rather hard example, but any questions so far? You just use KCL, KVL, okay, with things like this. Use a little bit of KCL, KVL, you got it. All right, how are you guys feeling about the topic so far? Difficult? Iffy? Okay, okay. It's I actually combined, so we're actually making good time. We finished 50-minute worth of materials in about 30 minutes. So the rest of 20 minutes, we can go into our next. So this is actually the next discussion. Whichever we get done, and then we'll let you guys go early, like next week. Let's just see how much we can get done this week. So this is called a non-inverting amplifier, which is like we talked about it earlier, that when we feed a signal into the input, we're getting this output, but it's the flip signal, right? So we always want to be able to control everything. We're control freaks in this case. And we want to be able to even control the sign. So the way to do that will be making use of the positive signal. So this is the inverting, right? And we proved earlier that the A is like negative of some sort of R over R. R something over R something. But you always have that negative sign. You can't get rid of it because you cannot pick a negative resistance. There's no such thing as a negative resistance. So you have to solve that issue by using your positive, your non-inverting terminal as your to make your analysis. And the way to do that is your circuit looks like this then. And this is actually a lot of times, this is the circuit I use, right? I want a non-inverting signal. I don't want to have, like when I put in a signal to play notes, it all of a sudden start playing the opposite things. I don't want that. I want whatever I'm putting in as control, it's just an amplification of the exact same thing I have. Right? I don't want to be pressing a button on my remote and then the TV amplifies like an opposite action and I want it. I want the same action, which is why we use a non-inverting. And the non-inverting signal, I'll just do the quick example here. Same steps in analysis. So if I define this point to be V1, okay? Can you guys tell me what V minus will be? V1, right? V1. And V plus will be V1 immediately. But what is the key observation here? This is also V in, right? So we actually got lucky this time. V1 directly, we got V in, which is... So from that, you deduce that V1 is actually equal to V in. So over here, we'll write that out. And notice something very interesting here. You have V naught over here. You have V in here. And then we take this portion of your circuit, you realize this is voltage divider. Very nice. So your V in equals to V naught times your, how does that equation go? R2 over R1 plus R2. Very nice. You guys didn't forget about that just yet. All right, keep that, make sure that's memorized. And V naught, and this is actually, so that's, V over, I'm gonna erase that because it's repetition. But we're looking for V naught over V in. So we'll first divide the V naught over to get R2 over R1 plus R2. And then we flip it, right? So your A will just be the flip version of it. V naught over V in equals to R1 plus R2 over R2, which then gives you this very, very famous formula that we'll be using. A equals to 1 plus R1 over R2. Did I hear it right? Yeah, okay, yeah. Now that's gonna be what you use to control, okay? So what's the big takeaway here? If let's say, so what's the big takeaway here? So my question is, if you can only control R1 and R2, can you ever get your output signal to be less than your input? Is it possible to have, yeah, it's impossible, right? It can only be 1 or above. So that is the caveat of using a non-inverting output, is that unlike the negative feedback cycle, which you can actually have smaller signal than what you intend to be, you cannot make this smaller anymore. The only signal that's going to come out of it is going to be something larger, okay? So that's that. Another question that I have is that, so any question with this so far? Good? Feeling good about it? So yeah, when you in the exam, when you see something wired into plus, you know that's non-inverting. A question I have for you guys is, what would be a good choice of R1 and R2? I don't care about amplification right now. I just say, would it be a better idea to choose R1 equals to 5 ohm, R2 equals to 6 ohm, or R1 equal to 5 kilo ohms, and R2 equals to 6 kilo ohm? Which choice is better? No, I'm just saying, like, for these two components, what let's just say that we're trying to get a gain of 1 plus 5 over 6. Okay, we're trying to reach that, so it's 11 over 6. We're trying to get this gain. Is it a good idea for me to use these two to reach that, or I use these two to try to get that? They give you the same, like, don't get me wrong, they give you the same amplification factor. So nothing's going to be different in terms of your amplification. But which one is a better choice?
The kilo ohms?
Why would be the kilo ohms?
Because if it's off by like plus or minus 1, it won't always make a difference.
That's a good point. That's true. But also, when you have a smaller ohms, the tolerance is by percentage. So you actually wouldn't be that off. Yeah. So that is a good point, but it's not the main reason.
Lower operating voltage.
What do you mean by lower operating voltage?
It's like safer.
How is it safer? Wait, which one? Which one did you pick?
Kilowatts.
Why would the kilo ohm be safer?
If the resistance is higher and oh wait, no, never mind.
What's your point? What's your opinion?
There would just be a lot less current running through it.
Okay. Which one will be the one that had less
With
current?
the kilo ohms,
Okay.
you have a lot less current.
And what does that mean? Like, I guess you already answered the question at this point. So you have a lot less current running through the loop, right? So with 5 ohm, let's just say that your output signal is 30 volt. With 5 ohms, you're already driving, like, what is it? Well, this is 5, this is 6, this is like 10, 11. So you're 30 volt divided by your like 10 ohms, you're driving like 3 amps already. Okay, so that's a lot of amp. Normally your cell phone is like, cell phone charger is like 502 amps. It doesn't even go over that. So just by doing that, and the biggest problem is not even the fact that the circuit is like safer or not. Even if your circuit is beefy enough to take it, the biggest problem is you only have a finite amount of current coming out of here. You're gonna split off the majority of it going through it just to get you that control. What about the other components you're trying to drive? What about if I put let's say like a 5,000 ohms of something like a light bulb, okay? You have 10 ohms of resistance here, and you have 5,000 on the other side, and you're like, man, the electrons coming out of the port is like, I'm going to take the path of least resistance. I'm going to go through the 10 ohms completely, leaving nothing going through the 5,000. Yes, you got your control signal all right, but it doesn't do anything at that point. It's wasted. It's all sent to the ground for nothing. So you want to have high resistance, so you want to preserve. You can get that voltage, but you can preserve the current for other use. Okay, that makes sense? All right, so the last part, we're almost done actually. 3 more slides, 3-4 more slides, and we're done. Yeah, we're moving pretty quickly, and I like it. So now we're talking about putting the complex stuff in it instead of just the resistance, right? We talked about using the resistor to control your signal, but we can also put phasors in there, and it also makes op-amp very interesting. Impedance is like resistance, but generalized to all components. We learned that many, many times in this course. And it's the same analysis technique. Z equals to V over I. You know, this equation, you probably know this by heart by now. You analyze it the same way, put everything into boxes, and then turn everything into, so, you know, you have a complex signal, you put it into like A plus BJ, then you divide it by your impedance, which is also some form of A plus BJ, gives you your current, and then you have maybe, you know, if this is wired to ground, you have 0 volt, this is 0, you have some sort of A plus BJ here, right? And then you define an I. You do the same thing we just did. Okay, does that make sense? And if they're asking you what is your V out over V in, that's the same thing as we did earlier, except that this is a complex version of it. So it might be like A1 plus B1J over A2 plus B2J, but a general form like that. It might look really messy depending on what kind of components is thrown in there, but you can get something like that. And this is how you get, like, if you put like even if you put some sort of a DC signal, if you have a bunch of these weird components in there, it might give you an alternating output. And in my suspicion is that this might be some of the ways how the voltage generator is able to generate like different waveforms, right? The waveform generator you use in Hesse Hall, it's just a very complex version of this. They're able to put in a DC signal, and it's giving you waveform, any shape you want, by just changing maybe the resistance and the impedance capacitance inside of it, okay? Does that make sense? This is just a op-amp, but with the on steroids, okay? Op-amp with impedance. All right, so this is a quick example. We'll quickly go over this. 10:52, we're almost done. So, all right, tell me by now, what is V plus? That's right. Okay. If anything you learned in this class, that is a dead giveaway. That's the easiest part of the problem. You go in there and you realize this is 0. Okay, this is 0. Makes your life much easier. This is your V naught. And then over here you define an I, and then we can, by this point I can already tell you guys, since there's no way for this to go, if this is I, they have to be the same I throughout the entire current. Make sense? So you're gonna have I equal to I, which honestly, you'll be your 0 minus V in over ZR1 plus ZC. Does that make sense? Impedance add, right? On the series circuit. That would be V naught minus 0 over ZR2 plus ZL. Okay? You get that. It's the same thing we did earlier, and you get your V naught over V in. And then that would just be your, this multiplied over with ZR2 plus ZL. Negative actually, because this is a negative feedback cycle. Do you recognize that? Negative feedback cycle over ZR1 plus ZC. Okay, make sense? That will be your transfer function. And if you have complex components in there, you notice how now the transfer function becomes something complex. So it's not just like feeding whatever you have, it feeds exactly the amplification version of it. It might be changing in time. So that will be what this component means, okay? Lastly, before we wrap up this class, first of all, any question with this so far? All right. Before we wrap up our this is actually the end of the formal discussion slides. I want to ask one more question is, when you have an op amp, what happens when you connect multiple op amps? Oh, that's interesting now, right? Because what happens when you do that?
Is the output, is the V naught of the first op amp forced to 0?
No, it actually won't be. Well, if you put a ground right here, it will, right? Obviously, but if you put a V2 here, this will just be some middle point of V0. Well, this is a V naught, right? This is your output right here, and this is your V, let's say intermediate. This V intermediate will be a middle ground, so that it satisfies this condition and it will satisfy here, right? So you can say I have 2 voltage here. And that V in will be fed again back into this circuit and get you the final. So whatever it is, it will just be. So when you now analyze such circuits, the first thing you do is you start from the bigger circuit first. Or you can start from the small, it doesn't matter. But it's good to start from the bigger one, the more final one. So you get your expression between your V int, V naught over V int, and it gives you that expression. Then what you do is you take your V int, you find your V naught 2. So we're not confused. You find your the thing between your V in t equals to whatever it is, V naught 1. And then you take yet again your V naught 1, you say what is the relationship between V naught 1 over V in. And then you substitute this step by step back in here to get your V naught 2. That make sense? So that will be how you analyze. I know I'm going through this very quickly, but that's how this will go. Basically, you take, and then you'll get more practice out of it as you do more problems. You're just taking these components. You're trying to analyze it step by step, and this is actually very useful because when you have an op amp and you have another op amp, if you don't put anything in between, you just wire one over the other one. Their gain actually multiplies. So A1 will just multiply by A2 if you directly connect them. So if you put like 3,000 of them together, they amplify it by whatever your gain is, multiply all together. Okay, does that make sense? So when you put an op amp like that with an op amp like that together, this is A1, this is A2. A1 A2 multiplied. So your A overall will just be your A1 multiplied by A2. Okay. You multiply the magnitude. Okay, so that wraps up the ME 100 discussion, everything. So from this point, do you guys like the discussion so far, relatively speaking? Okay, good. I know towards the end of the semester, people just stop showing up, but I know there are other exams. Do you guys feel like there's anything I